All right, some more on extreme values. We're going to try to, figure out how to find them, how to find the highest or the lowest value of a function. Well, let's start with this. Let's start with the extreme value theorem. Extreme value theorem says if f of x is continuous, right? Continuous means that at every point the function value is equal to the limit as you go to that value. The net result is you can draw the graph without picking your pencil up, right? If f is continuous on an interval, closed interval from a to b, right? So it's even at the endpoints continuous. Then f attains an absolute max and an absolute min somewhere on the interval. If f is continuous on a closed interval, so you've got some starting point here, some ending point there, so this is A to B, and I'm going to draw a graph. I can't pick my pencil up. Oops, sorry, I picked my pencil up. Let's go back here and say can't pick my pencil up. That somewhere there has to be a highest point and somewhere there has to be a lowest point. Right? If the function is not continuous, then all bets are off, right? That is, I can draw a function like this. Here's A, here's B, and you got a vertical asymptote somewhere in the middle there. So there's no absolute maximum because it goes up forever. There's no absolute minimum because it goes down forever. You can even, say at this point it's defined, so give it a function value. So it's defined at every point. It's just not continuous. Even still, we can do things like, even without an asymptote, you can do something like this and put an open circle there and an open circle here and like that. There may be a limit from the left and a limit from the right, but there's no actual value. It doesn't get up to this value. It gets arbitrarily close to it, but it never gets to that height there. So there's no maximum, there's no minimum. So if function is not continuous, then you're not guaranteed a max or a min. Also, if you have an open interval, so if the endpoints are not included, just think about something like this, where the endpoints are not included. It has no maximum because the maximum would happen at the endpoint, which isn't there, or it has no minimum because the minimum would happen at an endpoint, which isn't there. So if you have both a closed interval and a continuous function, then you're guaranteed a max or a min. I always like it when the book does this. It says, well, although this seems rather intuitive, it's kind of hard to prove, and so we're not going to prove it. Actually, if you get to an analysis class someday or topology class, this is a more general theorem where they talk about f is a continuous function on what's called a compact set. A compact set is closed, so it includes all its boundary points, and it's of finite measure. So a line segment here is only finitely long. And actually that gives a point here. I mean, when I could talk about the whole real line. Look at the exponential function. Right? It's defined on the whole real line. The whole real line is closed, but it's not finitely length closed. It has no maximum value. It has no minimum value. It almost has a minimum value because it's certainly bounded below by 0, but it never gets down to 0. So you need the finite length, you need the closed end, the endpoints included, you need a continuous function. You've got all those things, then you have somewhere a max and somewhere a min. Okay. Now the question is, where are those? Where are those maxes and mins? And so we have another theorem which is called Fermat's theorem. This is the same Fermat's last theorem, but Fermat's last theorem, of course, he never proved. He claims he had a proof, but it's now Wiles's theorem. But this theorem that Fermat did prove, and it says if f of x has a local maximum or minimum at x equals c, then, and f prime of c exists. Then f prime of c equals 0. So if you have a local max or min, and the derivative exists, then the derivative has to be equal to 0. Notice this doesn't go the other way, and we'll give you some examples in a moment here. But let's do a quick proof of this. Proof. Take a look at let's assume we have a local, let's say min at x equals c. The only difference between local min or local max is there's some inequalities that are going to be one way or the other. So let's just assume we have a local min. Take a look at the limit as h goes to 0 of f of c plus h minus f of c over h. Notice this is equal to f prime of c, right? Now when I look at that limit, if I look at the left-hand limit, h goes to 0, not x goes to 0. So if I'm approaching 0 from the left, h is negative, right? And this f of c plus h minus f of c, well, if they've got a local min here, then f of c is smaller than f of c plus h, right? So this is the smaller value, this is the bigger value, and so this difference here is positive. So so I've got a positive number on the top here, and I've got h on the bottom, but h is negative. So this is definitely a negative value, and this must be less than or equal to 0, right? This limit from the left is going to be less than or equal to 0 because you got positive divided by negative. It's got to be, at worst 0, but otherwise negative. On the other hand, if you look at the limit as h goes to 0 from the right, same limit here, c plus h minus f of c over h. Well, again, this is still positive because there's a minimum value at c, and so this is going to be still positive on the top. But as I'm approaching 0 from the right now, h is also positive. And so positive divided by positive is going to be bigger than or equal to 0, right? Because I know that this exists, I know that these two limits have to be equal to each other. Well, this first limit is less than or equal to 0. The second limit is greater than or equal to 0. The only way that they could be equal to each other is if they're actually equal to 0, right? So f prime of c has to equal 0. Right? In the event that, if this didn't exist, then I wouldn't be able to make a conclusion here. But knowing that the derivative exists at c tells me that this limit and that limit have to be the same, and so I can say that if one's less than or equal to 0, one's greater than or equal to 0, then they've got to be both 0. Okay. So if you've got a local minimum, the derivative has to be 0. To do a local max, all I would do is say, if this is a max, then c is the big one, so this is negative on top, and this is negative on top, and so I'd have to turn these both around, but the idea is still the same. Okay. If you've got a local max or min, and the derivative exists, then the derivative is 0. Now notice the converse is not true. Converse is not true. That here's two examples. Look at f of x equals x cubed. Right? If I take the derivative, 3x squared, I notice that at x equals 0, f prime of 0 equals 0. So there's a spot where the derivative is 0. However, that's not a max or min. Right? The graph of y equals x cubed looks like this. There's a horizontal tangent line there at 0, but I don't have a max or a min. So just because the derivative is 0 doesn't mean you have an extreme value. However, in another example, look at the absolute value function at x equals 0. Absolute value function. There definitely is a local minimum, even there's a global or absolute minimum at x equals 0, but the derivative isn't equal to 0. Right? So you can have a local minimum without having the derivative of 0. You can have a derivative of 0 without having a local minimum. However, if you have a local minimum and the derivative exists, or local maximum and the derivative exists, then the derivative has to be 0. Okay. In the next video, we will look at using all this stuff to actually find maxes and mins.